In this video, I'm going to talk about how to factor expressions using the difference of squares. So the difference of squares just means that we're subtracting two terms, so the difference, and then the two terms that we're subtracting are actually both perfect squares. So in this one we can see that this is x times x minus 6 times 6. So we can see that yes, indeed, they're both squares. Okay, so we ask ourselves, what got squared in order to give us x squared, and what got squared in order to give us our 36? Well, x was squared to give us x squared, and 6 was squared to give us 36. So we have a formula that we can use to do this. So we have a squared minus b squared, and it's going to equal the quantities a plus b times the quantity a minus b. So basically this is saying what got squared to give us our a squared and what got squared to give us our b squared, and the square root of each one of these terms is going to go respectively into their positions. So if we're saying that a in this context is x and b again in this context is 6, then it's going to be x plus 6 times x minus 6, and that's going to be x squared minus 36 factored. You can also think of this another way, and let me just jot that down again. This is a quadratic expression because the degree is 2, and we could write this as x squared plus 0x minus 36 if we wanted to include the linear term there. So when you're factoring quadratic expressions where the leading coefficient is just a 1 right there, you say to yourself, what two numbers multiply to make negative 36 that add to make, well, 0? Well, if they add to make 0, we know they have to be additive inverses of one another. So it's going to be 6 and negative 6. So we would just set up our factors like that. But if you notice, that's the same thing we had before. So factoring x squared minus 36 will give you quantity x plus 6 times quantity x minus 6. In this second example, we have 2y squared minus 50. So I notice it's the difference here because there's two terms that are being subtracted. But 2y squared and 50 are not perfect squares. Oh, but I do see that 2 and 50 are both even, so I could factor out a 2. When I factor that 2 out, I'm left with y squared minus 25, which, these are perfect squares. So you ask yourself, what got squared to give me y squared? And what got squared to give me 25? Well, y was squared to give me y squared, and 5 was squared to give me 25. So in our formula of a squared minus b squared, that equals the quantity a plus b times quantity a minus b, as we saw previously, the a is going to be y, and the b is going to be 5, and we can just plug those numbers right into the formula. So y plus 5 and y minus 5. And that'll be how we factor 2y squared minus 50. On to the third example here, we have m to the fourth minus n squared. So again, we're going to use that formula that we've been using so far. So a squared minus b squared equals the quantity a plus b times the quantity a minus b. So we have to ask ourselves, what got squared to give us m to the fourth, and what got squared to give us n squared? Typically these are the easiest because n got squared to give us n squared. But we have to ask ourselves, what got squared to give us m to the fourth? Well, you could say 4 divided by 2 is 2, so you could say m squared. Or you could think to yourself, because of this power of a power sort of thing, these two get multiplied to give us 4. So you just got to kind of work that math out in your head, simple arithmetic. So once you do that, then the m squared becomes the a, and the n becomes the b. And really you're just going to say m squared minus n times n squared plus n, just like that. In this fourth example, we have 9r cubed minus 4rt squared. So again, it's the difference, and we have two terms, but they don't appear to be perfect squares immediately, but I do see they both have r's, so I could factor an r out of both of them. So it'd be 9r squared minus 4t squared. And then, yeah, I do notice now that each one of those terms is a perfect square, so that I can factor this as difference of squares, rather. So what did I square to get my 9r squared? And what did I square to get my 4t squared? Well, the r and the t are easy enough. I can just put it like that. But what got squared to give me 9 is 3. And what got squared to give me 4 is 2. So my 3r is going to be my a, and my 2t will be my b. So it's just a matter of 3r plus 2t and 3r minus 2t. And then we can't forget this original expression. We factored an r out, so that r is going to go right there. So there's the complete factoring for 9r cubed minus 4rt squared. In this fifth example, I have x to the fourth minus 81, which seems to be a pretty straightforward difference of squares. So what got squared to give me x to the fourth was x squared, and what got squared to give me 81 was 9. So I'll have x squared plus 9 and x squared minus 9. Well, so this is the factoring of this, but it's not complete, because inside here I have x squared minus 9, which appears to be another difference of squares. So they're kind of embedded into each other. So this x squared plus 9 can't factor, because there is no factoring for sum of squares, because this is prime. But I can do x squared minus 9 and get x plus 3 and x minus 3. So the complete factoring for x to the fourth minus 81 actually has three different quantities that are all being multiplied together. It's x squared plus 9, and these other two, the x plus 3 and the x minus 3, we factored and found because we had this x squared minus 9, which on the initial difference of squares, one of the factors was another difference of squares. So always make sure to watch out for that when you factor it.